In semester 1, we learn mostly about polynomial functions. So we learn things like y equals x or y equals x squared, where we have the base, that's the unknown, and we have the exponent with numbers. In chapter 4, for exponential functions, growth and decay, what we're going to see is that the unknown variable is going to be the exponent. So we're going to have a number for the base, and then we're going to have that exponent be the unknown variable. So we're going to see things like y equals 2 to the x or y equals 1/3 to the x, again where the exponent is the unknown variable. Here are the things that you need to be able to do for 4.1. Set up and solve word problems. And given an exponential function, identify these types of things, as well as identifying whether something is an exponential growth, decay, or neither. Let's start with an example. Let's say you're in biology lab class and you are growing bacteria. You start with a single bacteria cell and it doubles itself every hour. The question is, how much bacteria will you have at the end of 24 hours? Well, let's see, at the end of the first hour, you're going to have double what you had, so you're going to have 2. At the end of the second hour, you're going to have double that, so you have 4. At the end of the third hour, it's going to be double, so 8. At the end of the fourth hour, it's going to double again, so it's going to be 16. So notice that we're doubling each time, which means we're multiplying by 2 after every hour. So the pattern is, here we have 2 to the 1, here we have 2 times 2, so 2 squared. Here we have 2 times 2 times 2, so 2 cubed, 2 to the 4th, meaning at the end of 24 hours, it'll be 2 to the 24th. And when we write that down, or when we calculate that in our calculator, we'll see that it's 16,777,216 bacteria that we would end up with. I can write this as a function, so that's y equals 2 to the x, right? Because notice if I plug in 1, I get out 2. If I plug in 2, I get out 4. If I plug in 3, I get out 8, right? 2 cubed, and so forth. So notice that the base right here, that is how much you're multiplying by each time. So because I'm multiplying by 2, I'm doubling each time, you're growing what you have. So this is an exponential growth. So the way you know whether what you have is an exponential growth or not is you look at the base, and that's the number you're multiplying by. So if you multiply by that number, are your total values going to get bigger or smaller? That's how you can tell. So this is an example of an exponential growth. Let's take a look at what this might look like if you were to make a table and graph it. So if I plug in 2 to the 0, that's 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the negative 1, remember negative exponents flips it, making it reciprocal, it's 1/2. 2 to the negative 2 is 1 over 2 squared, so 1/4. And 2 to the negative 3 is going to be 1 over 2 cubed, which is 1/8. If I were to plot this, this is the type of that graph that I'm going to get. Some things that I want you to notice is that as you go 1 unit over to the right, for every unit you move to the right, your y value doubles. Here I'm at 1, then I'm at 2, then I'm at 4, then I'm at double that, which is 8, then if I move 1 unit over, I'm double that, which is 16. And that happens because my base here, right, is 2, and that tells me that every time I move to the right 1 unit, I'm going to be doubling my y value. Something else I want you to notice is as you get smaller and smaller, or as you go to the left of the number line here, right, you get -1, 2 to the negative 0.5, 2 to the negative 2, right, that's 1/4 or 0.25. Notice that the numbers get smaller and smaller. They actually get closer and closer to the 0, but you don't quite reach the 0. So we have a horizontal asymptote right here at y equals 0. You have a horizontal asymptote because as you go towards negative infinity in the x direction, your y value gets closer and closer to 0. Let's talk about the domain. Domain is going to be all real numbers, and the range is going to be y is greater than 0 because all of your points, all of your values are above your horizontal asymptote. Okay, let's take a look at another example. let's say you're at a tennis tournament with 128 players, and half of the players are eliminated every round. It makes sense, right? You play against one other person, you have a winner and loser, half the people get eliminated. It asks how many players remain after 5 rounds. Okay, so you start with 128, and after the first round, you lose half of the players. So you're gonna end up with, whoopsie, you're gonna end up with 64. Half of 128 is 64. Then people play again, and at the end of the second round, you're gonna have half of 64, so that's gonna be 32. Half of that, right, gives you 16, half of that gives you 8. So by the end of round 5, you're going to end up with 4 players. So notice here that we are dividing by 2, but you want to think in terms of what you're multiplying by. Dividing by 2 is the same thing as multiplying by 1/2. So that's going to be our base. Our base is going to be like 1/2 to the x. Because again, as you go over 1 unit to the right, as you increase by 1, what's happening to your overall value or to your y value? It's dividing by 2, or it's multiplying by half. It's halving. So that's what your base is going to be here. So that's going to help us with a pattern here. We know we're having, but we didn't start with just 1. What did we start with? We started with 128. Let's see if I can move this. There you go. So the way we got 64 is 128 times a half, right? And the way we got 32 was having that, which is going to be 128 times a half square, because it's 128, right? It's 128 times a half, which is this step right here, but then we have to multiply by that, by a half. And then if we keep going, you're going to notice that, right? This is the pattern that we get, right? So 128 is how much we started with, and then we half. We multiply by half for every time period. So this right here would be the function that represents the word problem here, and this would be an exponential decay, because you are decreasing, you're decaying, you're halving each time. So again, I look at that base there, and that's going to be a decay factor, because every time I multiply it by a half, my overall value gets smaller, not bigger. One other thing I want to mention is just because you're decreasing doesn't make it automatically an exponential decay. So for example, if I have y equals negative 2x, I know that I'm going down 2 over 1, so I know that I'm going to have some kind of a decreasing graph or decreasing relationship, but that's linear, not exponential. What makes something exponential is that you have a constant percent increase or constant percent decrease. So 50% decrease each time, or like 100% increase each time, right? But we write it as a decimal or a fraction, right? So it has to be a constant percent increase or decrease in order for something to be exponential growth or decay. Okay, here's a Desmos graph of the function that we just looked at. And again, we started with 128, and every time we move over 1 unit, we're going to have half of what we have. So that was 64. Move 1 unit over, we're going to have half of what we had, which is going to be 32. Move 1 unit over, half of that, so that's going to be, what was that, 16. Half of that, we're going to end up with 8, and then 4, 2, 1, 1/2, a fourth, an eighth, and so forth. Again, notice that we get closer and closer to 0, but we don't quite reach it. So we have another, horizontal asymptote here at y equals 0. It's one-sided, really, but you still say that you have a horizontal asymptote at y equals 0. So your values are getting closer and closer to 0, but not quite reaching. Again, domain in this case would be all real numbers. You have all the x values that you can plug in and see in your graph. Range, again, all of your points live above your asymptote, so it's going to be range as y is greater than 0. Okay, let's take a look at a couple examples. Is the function exponential growth, exponential decay, or neither? Let's say I had y equals something to the x. Again, that's how you recognize something's exponential, because the variable is the exponent. You have a number for a base. Let's say I had like 5. Is this going to be exponential growth, decay, or neither? Well, I know because my base is 5 that I'm multiplying by 5 each time I move to the right 1 unit. So when I multiply by 5, my numbers get larger exponentially, right, by a factor of 5. So that's really a growth factor. So I know this is an exponential growth. So if I were to graph this, you would still have my horizontal asymptote here, but I know I would be growing exponentially. Just a basic sketch, okay? What if I have something like 1/5 on the inside, right? So instead of 5, what if I have like 1/5? Again, I know this is exponential of some sort because I have my variable in the exponent and I have a number for the base. I know that I'm multiplying by 1/5 each time. And when I multiply a number by a fifth, right, my numbers get smaller and smaller, so I know this is going to be exponential decay. So if I were to graph this, I know, again, I have a horizontal asymptote, and because it's decaying, it's going to be looking something like that, right? You get smaller and smaller, getting closer and closer to the asymptote there as you move to the right. So when would you have neither? So the way that I'm going to be asking you is the following. What if I put like a negative out here? Okay, do you remember what kind of reflection that is? It's going to be a vertical reflection or a reflection over the vertical or over the x-axis. Okay, so notice when I have this graph here, the relationship is no longer the same, right? Notice that I'm not multiplying by the same number each time. I'm not like I'm not multiplying by a 5. I'm not growing by a factor of 5 as I go to the right, or decreasing by a factor of 1/5 as I go to the right. So that would be a case where it's neither. If you have a negative out in front. Again, same thing here. If I have a negative out front here, then it's going to be a reflection over the x-axis. And this is no longer an exponential relationship. It's a reflection of an exponential decay, but it's not exponential. Because as I move 1 unit to the right, I'm not like growing at a constant percent. Like I'm not growing at a constant rate or a constant percent rate, like tripling every time or halving every time. That's not happening, because notice right here, it's growing faster and faster, and right here, it slows down. So it's not that's a constant percent. So again, if you have a negative out here, whether it's a -1 or like a -3, or a -1/3, if you have a negative, because it's a reflection, it is going to be neither. The correct answer to this question is B. B is the only one with a base that is less than 1. So every time you multiply by 10/11s, you're going to get a smaller number. The other ones don't. This one was a little tricky, 1/1/2. That's really just 2, so that would have been exponential growth. And none of these are reflections because they don't have any negatives out in front, so we're good. B is the correct answer. Last part. When you're given a word problem, you need to be able to write the word problem as a function and then solve it. So for example, if you want to model growth or decay by a constant percent increase or decrease, this is like a formula that you can use. This formula will not be provided for you on the test, so you do need to know it, but it's pretty straightforward. I know there's a lot on this page, but hopefully I'll explain it and it'll make more sense. So 1 plus r is what you use when you have a growth factor. You use 1 minus r if you have a decay factor. So let's think about, let's go back to the example we were looking at the very beginning. Remember the one where we had the bacteria example? So let's think about it. If you wanted to write that using this model here, we would start with, well, how much bacteria would you have? You would have, well, how much did we start with? We started with 1 bacteria, so that's your initial amount here. And then you put a 1, and because we're growing the bacteria, right, remember we're doubling after every hour, we're going to put the plus sign here. And then here, the R is the rate of increase. So remember, we're doubling. So that's 100%, right? Because you go from 1 to 2, so you're doubling by 100%. You need to put that in decimal form. So 100% in decimal form is going to be 1. And then T is a time period, so you're just going to write that there as a T. So that's A equals 1 times 1 plus 1, which is 2, 2 to the T, or just A equals 2 to the T. Remember, we had it as y equals 2 to the x for the bacteria doubling, because after one time period, right? T, A equals 2 to the T, right? After one time period, you have 2, right? After 2 hours, you have 4. After 3 hours, you have 8. See how you're doubling each time, okay? So that's the formula. And then you need that 1 in there, because if we don't have that 1, it's not going to work out for us. So for example, sometimes students do this. You're like, oh, I start with 1 bacteria, and then I know and then the rate of increase, let's say it's like 1. That's not going to work out because you're just always going to have 1, right? If I plug in 1, I get out 1. If I, right, T and the amount. If I plug in 1, I get out 1. If I plug in 2, 1 squared is still 1. If I plug in 3, 1 cubed is still 1. So you need to have that 1 there for the base, right? Because you're multiplying by 100% plus whatever the percent increase or whatever the constant rate is. Okay, so let's take a look at that second example now. The example with the tennis players. Remember, we're trying to figure out how many players we're going to have after 5 rounds. Well, we start with 128, so that's our initial amount. So 128 is what we start with. And then right here, again, we have that 1. And this time we're decreasing. We're going to have a decay factor because remember, the people are going to be halving. Like there's going to be winners and losers. So you're going to be losing players, so it's going to be minus. You are losing 50% of the players, so that's going to be 0.5. And then let's say we have like T, whatever the time period is. In this case, after each match. So that's A equals 128 times 1 minus 0.5, which is 0.5 or 1/2 to the T. That will be the function. And if I were to ask you, how many players are left after 5 matches or 5 rounds, you would have to plug in 5 for T, right, and plug into your calculator, and you would get out, I believe it was 4 players. The correct answer for this problem is B. You start with 89,443. You increase, so it's plus, and right here, remember you got to change the percent into a decimal format. So 1, 2, so it's going to be 0.006 to the T, which is, when simplified, 1.006 to the T. So it's going to be B.